Thank you. Welcome everybody to the last talk of our workshop. In this talk, I will present some recent results from our group about computing rational solution of a first-order algebraic ordinary differential equation. The structure of the talk will be as follows. First, I will clarify the problem that we are working. Then, I give her an idea by Aramanko about this problem he presented before. And then, I will propose 3 different approaches to attack the problem. Each approach will give a different result. Okay, let's first state the problem and the result we obtain today. By K, we mean a computable algebraically closed field. In bracket, the K will be the field of algebraic number, or the field obtained from algebraic number by a constant. But anyway, it is a computable algebraically closed field. And a first-order algebraic ODE is a differential equation of the form f x y y prime equals 0, where f is a polynomial in 3 variables. A rational solution, of course, a solution in K, solution which is a rational function. And the problem is that given a first-order algebraic ODE f x y y prime equals 0, we're trying to propose an algorithm to check whether the differential equation have a rational solution or not. And in the affirmative case, compute all of them. We haven't completely solved the problem yet. We just have some partial result, and the problem is still under integration. Well, we solve a problem in the class of first order, first degree, and we also solve a problem on the class of first order algebraic ODE, where the f defines an algebraic curve in the alpha plane over kx bar, the field of algebraic function over k of sinus 0. And we also solve the problem in a generic class of first order AODE, which we say maximally comparable. I will explain later what is a maximally comparable first order AODE. Okay. About the problem, there was a very nice idea by Aramanko around 15 years ago. He proposed an idea to give an upper bound for the degree of a rational solution of a first order AODE. And let's consider what is his idea shortly. Aramanko consider first order algebraic ODE whose coefficients are complex numbers. Actually, he worked for algebraic solutions. For each algebraic function over C, he defined a number, an associated number he denoted by T alpha, which is the number of poles on each Riemann surface called the multiplicity, divided by the number of the seats of the Riemann surface over the Riemann sphere. Well, this number is a natural extension of the definition of the degree of a rational function. In particular, when the algebraic function alpha is a rational function, then the T alpha is the degree of alpha.
And the degree is the degree of the numerator minus
The degree of a rational function
Yeah.
is the maximal degree of the
both.
numerator and denominator. And Parametrization gave an upper bound of the alpha. That means he gave an upper bound for rational solution. And his idea basically based on the theory about classification of differential algebraic function field of transcendental degree 1. He considered the differential function field R, which is the quotient field of the ring defined by Cx bar Yz divided by the ideal generated by F. Well, let's assume that F is irreducible over Cx bar. Okay, and this, the field R can be a differential field by obtaining the derivation from Cx to the whole field R by the derivation of Y bar equals Z bar. Then Matsuda give a theory to classify the differential function to R up to isomorphism of differential field. In particular, if the field R is Fuchsian, that means the derivation map will map every valuation ring of the function field R to itself. Then the R will be isomorphic with one of the three cases. For the first case, R is a field of rational function over Cx bar, where the generator T satisfies a Riccati equation. It happens when the Z0 of R equals 0. When the Z0 of R less than 0, then it can be happen in two different cases. In the first case, R can be generated by T and T prime, where T is a solution of an elliptic function. Or R can be the field of rational function in two variable T, two elements T1 and T2, where T1 and T2 satisfy the differential system. Okay, that is the theory of Matsuda about classification of differential function field. And Parametrization, he considered the differential equation f equal y prime equals 0. And then he considered a differential function field R associated with F. He gave her a degree bound for the case when R is not Fuchsian. And then when R is a Fuchsian field, he gave her a degree bound for the three differential equation here. And then he obtained a degree bound for the whole case. However, he proved the existence of the bound. But to be possible to have an algorithm to compute such a bound, we need some modification.
Can I ask you something? So in the R, you said that y prime is z, right?
Yeah.
Do you say so? Z prime is
So Z prime is
close.
Y double prime.
So
Oh, it's over f. Okay. Okay. Fine.
Okay. That is the idea of Parametrization. So my work is try to modify the idea of Parametrization and combine with the other knowledge to produce an algorithmic way to actually compute such a bound. First, I try to use some combinatorial technique to attack the problem. We prove that for a given polynomial f in three variables, and assume that f is non-homogeneous at a polynomial in when z, then for every point x0 on the on the projected line, we construct a bound, say rho, depend only on x0 and f, so that every rational solution of the differential equation had a pole at least at a pole at x equal to x0 of order at most rho. Well, and the proofs in definition is it is a strict partial order on n squared, and it is not a total order. And the theorem says, let's consider the f polynomial in two variables. Now we consider f as a polynomial and in two variables y and z with the polynomial coefficient. And we consider the set of exponents, of term of f. If the set of exponents of f admit a graded element with respect to the order which might be 4, then let's say the graded element is I0, J0, then pole in case of a rational solution of the differential equation f x y y y equals 0 occur only at 0 of x0, y0. So, well, let's define the differential equation, satisfy the assumption that the set of exponents admit a graded element is maximally comparable. So what does it mean? So for a differential equation which is maximally comparable, we can easily determine the set of poles. For each pole, we can determine the order of that pole. Then we find our solution, our rational solution. For example, we consider this a random differential equation. Which is that this differential equation is maximally comparable with the exponent of the rest form is logic one. Then rational solution may have a pole only at 0 and maybe at infinity, and we compute a bound for the order of a rational solution at 0 and infinity, and then we have the form for a rational solution, and making an answer, we get our solution of this differential equation. The question is, how often a first order AODE is maximally comparable? We would say generally. That means if we choose randomly a first order AODE, then in most of the case, it is maximally comparable. So we obtain a first result, computing rational solution of maximally comparable AODE. Well, second, we will try to apply the first result to the plot of first order, first degree AODE, where prime equal to f0 xy over f1 xy, where f0 and f1 are polynomial in a and y. We check that a first order, first degree AODE like this is maximally comparable if and only if the difference between the degree of the denominator in y and the degree of the numerator in y different from 2. So we only need to consider the first order third degree AODE where the subtraction of the degree of the numerator and denominator equal to 2. Moreover, when the degree of the numerator is 2 and the degree of the denominator is 0, it is a recursive equation. Well, for recursive equation, we know that there was an algorithm by Kovacic completely solved problem for finding rational solution. So we can only assume that in this case, the subtraction is equal to 2 and the degree of epsilon equal to 3. And this case will be the hard part of the algorithm. And the idea we give here to create the AODE that satisfies this condition is a revision from the Kamke idea. We need some ingredient from algebraic function field theory, like prime divisor, place divisor, principal divisor. I will give a quick introduction about them. Well, let's say that which R is an algebraic function field of transcendental degree 1 over the field of algebraic function. When we say a prime divisor of R, let me repeat, that means a maximal ideal of a variation ring of R. And each maximal ideal of a variation ring of R will define a map from R to Kx bar, shown with the infinity point. And this map we define by a place. A place, we can understand it like an evaluation map. And we have a definition of divisor, which is an element of the abelian group with a basis over the set of prime divisor. And we also have a definition for principal divisor of an element in R. And we write U with square bracket minus, the negative part of the principal divisor of U. Okay. Quick introduction to notation. We need for a theorem as follows. This theorem is a modification of a lemma in elemental paper. It's a given two elements U and W in R, so that the negative part of U is smaller than the negative part of W of the principal ideal, the principal divisor of W. Then, well, let's see if is an irreducible polynomial defines the relation between U and W. We can only find such a C by problem-based computation. And we denote by L a field intended by Kx, and we zone the coefficient of C. Then L now is an algebraic function over K. We prove that there exists an effective divisor delta of L, so that when we evaluate U and W at a prime divisor, we get a new inequality in effective divisor of L, like this. Well, this is a theorem stated for algebraic function. Whatever it is, we need a translation from algebraic function to the rational function case. And now we get something like this, the corollary one. Given W and U and W are a rational function in Y, and we assume that U and V satisfy some conditions. That implies something like a rational above. That means the denominator of U divide the denominator of W, and we have a condition about the subtraction over the degree of the two. If the condition holds, then for almost all of Yx, well, then say I see a constant G, just that for almost rational function Yx, when we evaluate U at Yx and W at Yx, we have a inequality in the level of number. In the application, this one will be the degree of the solution, and this one will be the degree of the derivative of the solution. So let's see how we apply the corollary one to higher degree bound. Oh, anyway, the proof of the two are constructed to be sure that we are doing real computational point of view. Okay. We try to apply the previous corollary for some rational function appears on our differential equation. We try to first we apply with a pair of 1 to the n and f0. And second, we try to apply with 1 over f0 and f1 over f0. Then we obtain the two inequality. And the two inequality is true for almost every function y, whatever it is a solution or not. However, if furthermore Yx is our rational solution, non-constant, then we can do just some technical step, and we get a degree bound for Yx from the two inequality here. Then we have a degree bound for rational solution. Then we can compute all rational solution by making an ansatz. Okay. And so we have solved the problem of finding rational solution in the case of first order first degree. Next, I would like to present a geometric approach. That means using parametrization of algebraic curve to attain the graph of AODE, which we can find rational solution to the graph of parametrizable first order AODE. Let's see how we do it.
What is AODE?
How much time we have to
Algebraic.
About 5 minutes. What's the
5
second
minutes.
D?
Okay.
Algebraic ODE.
I mean, it's like, what's the hypo?
In the first line,
Oh.
ADODE, is the D
Ah,
supposed to be there?
I think it's just,
Oh.
It's
There's
a
an extra
typo.
D, there's a
Sorry, a
extra
typo.
Yeah.
Yeah.
Okay. Now, we are consider first order algebraic ordinary differential equation, only one D. Okay. We replace the derivation y prime by a new indeterminate. Then we get an algebraic equation f x y z equals 0. And we consider it as that we consider it by that it defines a corresponding curve, let's say by C, in the alpha plane over K bar. this approach, we need an additional assumption that the generality is 0 to be sure that we can do parametrization. And a parametrizable first order AODE is the AODE and it satisfies the additional assumption. Okay.
So you mean the family of curves with x parameter x, the parameter? What do you mean, fx?
So the coefficients of the curve lie in k of x.
But there's, oh,
So he's
Yeah,
thinking
yeah.
it's
so y, z are the variables.
Y and
right,
Z
right.
are
So
variables.
it's a curve
And
over
x.
kx.
Yeah.
Yeah.
Okay, okay.
Y and Z are variable and X are in coefficient field. Okay. So we are considering AODE, which satisfy the additional assumption that the g-naught of the corresponding curve are 0. Then we can use parametrization. Parametrization of the curve C is a pair of rational functions in T, with coefficients are algebraic function in X. So that when we plug in P1 and P2 into Y and Z, then we have 0. And the image of P is dense into curve C with respect to the Zariski topology. Just some day ago, we proved that every algebraic curve in the affine plane over K bar of C0 we define by a polynomial in F with coefficient of rational function in X is parametrizable over Kx. Last week, somebody asked me whether an algebraic curve of C0 is parametrizable over Kx or not. I would say no, in general, no. In general, we need a quadratic extension of the computation field. But I have no counterexample for it. Actually, I compute with around 500 examples by Maple from Kamke calculation about parametrizing the corresponding algebraic curve. And surprisingly, all of them are parametrizable over Kx. And now we can prove, we can propose an algorithm to compute it. In
Does
general,
this mean the curve has a kx rational point?
Yeah,
Yeah.
that's what you need, you just need a point, yeah.
no,
Yes, so it's the same as having a kx rational point.
no,
So any G0 curve of a kx has a kx rational point? It's the
yeah,
same. And this wasn't known before?
that is just right. Well, it's true if the K is algebraically close. Otherwise, if the K is not algebraically close, then it is wrong.
Oh, k is algebraically close.
Yeah.
Oh, I didn't know k was taken algebraically close. We went on.
He's assuming
Okay.
that was at the
Oh,
beginning.
begin, okay.
Then, now we can do parametrization with parametrizable first order AODE. How we do it? We will translate the origin first order AODE to the new one, which is first order third degree, and we do it as follows. We consider a parametrizable first order AODE. Now, we have an algorithm to actually compute a parametrization P1 and P2 over Kx. Then we state that a rational function Yx is a solution of the differential equation Fx by y prime is 0. If and only if one of the three following K happens. For the first case, the pair of y and y prime lie on the set C minus pt. And it is a finite set because pt is dense in C by the Zariski topology. And we actually can compute this set. Second, Yx equal to P1x omega x for some omega x is a rational solution of an algebraic system. Whatever it is just an algebraic system that we can compute on a rational solution by problem-based computation. And in the third case, yx equal to p1 of x omega x, for some omega, a rational solution of a first order AODE, which is depend on Thieu, P1. And this kind of differential equation is now solvable by rational solution from the previous approach. So, we give an example. We pick up a randomly differential equation in Kamke calculation. We compute a parametrization, compute C minus, immediately solve the associated algebraic system, and you see the associated differential equation now is easy to solve. So now show the three smaller problems and give an origin rational solution. Okay. So conclusion. We have proposed an algorithm for computing all rational solutions of first order AODE, which are either maximally comparable in the meaning from a combinatorial point of view. First order, third degree AODE, or parametrizable first order AODE. That means AODE whose corresponding curve is of genus 0. For general case, when the corresponding curve has a higher genus, we are studying. And the subclass of first order AODE, surprisingly, that it covers all first order AODE from Kamke calculation, around over 500 examples. And I finished the talk.
Are there questions?
Could you just show the last slide again?
The last,
The one before this.
this one.
Okay.
This one I started from first order AODE in degree 3. I compute a parametrization of the corresponding curve.
Now, what I was interested in was an example where you have you have an infinite number of points, such that at each of those points you have a rational solution with a pole at that point.
Yeah.
Yeah, this gives an example.
Yeah. Yeah. In this case, we have an infinite rational point. On the curve.
Lots of poles. Yeah. Okay. Thanks.
Alice?
On the last slide, the last slide of the talk. Would you?
This one.
The other direction.
The other direction, yeah. The 3 bullet points, each next generalizes the previous. Is that right? Or am I confused? No?
Which one are you talking about?
The third generalizes the second, right?
The second one.
The third one generalizes
one.
the second one.
Yeah.
Okay.
Third order, third degree AODE is always parametrizable.
But the first one is in a different direction.
Yeah, the first one
Okay.
is the other direction.
Okay. Thank you.
Other questions? Let's give the speaker.
We should thank the organizers.
That's what I wanted. I
Yes.
wanted to thank Alice. and
Thank you very much.
organizing. The room is available for a while this afternoon in case people want to hang around and talk, which I certainly would encourage, and I'm sure the organizers would want that. So feel free to stick around a while. Have a good